Imagine a time when the world was at a brink of chaos. A secret project, shrouded in mystery, was unfolding. It was called the Manhattan Project, a name that was only whispered in the most confidential circles. It was here that some of the most brilliant minds came together, not just to innovate, but to unleash a power so immense it could alter the very fabric of existence. This project was a top secret endeavor during World War II, where the US aimed to develop the first nuclear weapons before Nazi Germany. This project spanned across three main sites: Hanford, Washington, Los Alamos, New Mexico, and Oak Ridge, Tennessee, profoundly shaping history and leaving lasting legacies. As the director of the Manhattan Project's Los Alamos laboratory, J. Robert Oppenheimer, born in 1904, played a pivotal role in the development of the atomic bomb. Known as the father of the atomic bomb, the New York-born theoretical physicist earned his PhD from Germany's University of Göttingen in 1927, later joining UC Berkeley and Caltech. Chosen by General Leslie Groves in 1942, Oppenheimer led the Los Alamos team in designing and constructing the first atomic bombs, achieving a breakthrough with a successful Trinity test in July 1945. The United States confirmed the atomic bomb's effectiveness, leading to an ultimatum for Japan's surrender and the decision to use the bomb against Japan. The uranium-based bomb Little Boy was dropped on Hiroshima, and the plutonium-based bomb Fat Man was used on Nagasaki in August, resulting in Japan's surrender at the end of World War II. Now, how is there so much power that it can destroy cities in seconds? To really understand this, we first have to ask, well, what is an atom? An atom is the basic unit of matter, the smallest component of an element that retains the properties of that element. Now, protons, neutrons, and electrons are tiny particles that make up atoms. Protons, they have a positive charge. The number of protons decides what type of element that atom is, like hydrogen, oxygen, and carbon. Neutrons, although they have no charge, they help stick the nucleus together and can change the atom's mass. Electrons, these have a negative charge and they move around the nucleus. They're much smaller than protons and neutrons. Now, electrons look like it's orbiting this atom right here, but they actually don't orbit. Because in the tiny world of atoms, things work differently than our own big world. Instead of having a fixed path, electrons are found in these fuzzy areas around the nucleus where they're likely to be, but not in a specific spot like a planet in orbit. It's a bit like a cloud where you know the electron is inside, but not exactly where. Now let's talk about atomic numbers. An atomic number is like an ID for an element. It tells you how many protons are in the nucleus of an atom of that element. For example, if an atom has one proton, its atomic number is 1, which means it's hydrogen. Each element has its own unique atomic number. Also, the atomic/mass number is the sum of the protons and neutrons. Now, where it becomes really fun is isotopes. An isotope is a version of an element that has the same number of protons but a different number of neutrons in its nucleus. This means isotopes have the same element, but they have different weights. For example, carbon-12 and carbon-14 are both carbon, but carbon-14 has 2 more neutrons than carbon-12, making it heavier. Now, you're probably wondering where I'm going with this, but just let me cook. Now, you're probably wondering why atomic bombs use uranium and plutonium. Well, many heavier elements with small binding energies per nucleon can actually decompose into more stable elements. This decomposition is called fission, the breaking of a large nucleus into smaller pieces. When a slow neutron hits a fissionable uranium-235 isotope nucleus, it is absorbed and forms an unstable uranium-236 nucleus. This uranium-236 nucleus then rapidly breaks apart into 2 smaller nuclei, in this case, barium-141 and krypton-92. This usually goes along with several neutrons, usually 2 or 3, and releases a very large amount of energy. Also, by the way, nuclear fission of uranium-235 produces a range of fission products. The larger fission products of uranium-235 are typically one isotope with a mass number around 85 to 105. And we also have another set of mass numbers, typically between 130 and 150, that is generally larger than 50%. And by 50%, I mean the fission yield. The process of breaking apart heavy elements like uranium-235 releases a huge amount of energy. For example, when we split just 1 mole of uranium-235, the resulting pieces weigh slightly less than the original whole. This tiny difference in weight turns into a large amount of energy, about 1.8 times 10 to the 10th kilojoules for each mole of uranium-235. Compared to everyday chemical reactions, like burning coal, the energy from splitting just 1 kilogram of uranium-235 is vastly greater, about 2.5 million times more. And here's the kicker. That's for the same amount of weight as the coal. It's such an incredible amount of energy, it's so hard to wrap your mind around. When uranium-235 splits, it forms 2 smaller nuclei and releases 2 or 3 neutrons. These neutrons can then hit other uranium-235 atoms, causing them to split and release more neutrons. This series of events is called a nuclear chain reaction, as shown in the picture. However, if these neutrons escape without hitting other atoms, the chain reaction won't happen. The balance between keeping enough neutrons to continue the reaction and losing too many is crucial for the process to work. Nuclear fission becomes a continuous process when the neutrons produced are enough to keep it going. This happens when the number of new neutrons matches or is more than the number of neutrons that are either absorbed during the process or escape out of the material. The smallest amount of material needed to maintain this balance and keep the reaction going by itself is called the critical mass. If there's not enough material to keep the reaction going, it's called a subcritical mass and the reaction stops. On the other hand, if the material is more than enough and the reaction starts to speed up, it's called a supercritical mass. Now, the actual amount of material needed for these states, critical, subcritical, or supercritical, varies based on several factors. These include what the material is, how pure it is, its temperature, its shape, and how the reactions of the neutrons are managed. All of these factors influence how easily the neutrons can keep the fission process going. Now, you're probably wondering, why are they using uranium-235 and not uranium-238? In fact, uranium's 2 natural isotopes are uranium-238 sitting at 99.3% and uranium-235 sitting at 0.7%. Why would we go through all that trouble to get uranium-235 when it's 0.7 of uranium's natural composition? Well, let me tell you why. Now, there's a couple main reasons why uranium-235 is preferred over uranium-238 for fission. Now, uranium-235 can undergo fission when it captures a slow-moving neutron. In contrast, uranium-238 is not fissile with slow-moving neutrons. When uranium-238 absorbs a neutron, it doesn't typically fission. Instead, it transforms into other isotopes like plutonium-239 after a series of decay steps, which are fissile. Another reason is the chain reaction capability of uranium-235. It can sustain a chain reaction where one fission event causes further fission events. It's critical in nuclear reactors and nuclear weapons. Like mentioned previously, when a uranium-235 nucleus absorbs a neutron, it becomes unstable and splits into 2 smaller nuclei, releasing a significant amount of energy and more neutrons. These neutrons can then initiate fission in other uranium-235 nuclei, creating a self-sustaining chain reaction. Uranium-238, due to its instability to sustain a chain reaction with thermal neutrons, doesn't serve this purpose. And thermal neutrons basically just mean slow-moving. Now, there's something else called the cross-section for neutron capture. The probability of a neutron-inducing fission in a nucleus is measured by the nuclear cross-section. Uranium-235 has a much higher cross-section for absorption of slow neutrons compared to uranium-238. This means that in a reactor or a bomb, where the neutrons are moderated to lower speeds, uranium-235 is much more likely to capture a neutron and undergo fission than uranium-238. Now, uranium-238 is not fissile with thermal neutrons, it can fission with fast neutrons. Fast neutrons are essentially higher energy levels. However, the probability of a neutron-inducing fission in its cross-section is a lot lower, and the energy required to sustain a chain reaction with fast neutrons is much higher. This makes the process less practical and more difficult to control than the fission of uranium-235 with thermal neutrons. And there you go! Now you're ready to go get a bunch of uranium-235 and we can start on this whole process. Ooh, I forgot to mention, we do have to separate those isotopes. You know, the 0.7% naturally occurring uranium-235 isotope. And this is exactly what happened at Oak Ridge, Tennessee during the Manhattan Project. Let's go into exactly how they did this. Now, one of the ways that they did this was from the Y12 electromagnetic isotope separation plant. The Y12 plant was built to scale up Ernest Lawrence's electromagnetic isotope separation process essential for the Manhattan Project. This technique, developed at the University of California at Berkeley, used a cyclotron, which is a type of mass spectrometer. This separated the lighter uranium-235 atoms from heavier uranium-238 atoms using a strong magnetic field. Okay, I'm going to get real with you right now. This is going to be a pretty complicated explanation, and I'm going to give you a simple one right after it, so feel free to skip to that part. When a beam of uranium ions, all with the same energy, goes through a magnetic field, it separates into different paths, one for each type of uranium isotope. This happens because the uranium types have different weights, so they bend differently in the magnet. At the end of their curved paths, there are special containers, like collecting cups, that gather each type of uranium separately. Basically, electromagnetic separation methods use magnetic and electric forces to manipulate charged isotope species. Here's how it works in simple steps. Number 1, they would prepare uranium gas, and they would use uranium chloride salt, usually uranium tetrachloride, and they would heat it until it turns into a vapor in a vacuum. Next, they would ionize it. The vapor is given an electric charge, turning it into ions, which are charged particles. These charged ions are then directed through charged slots to form a beam. The beam passes through a strong magnetic field, which makes the ions move in circles. The path they take depends on how heavy they are. Uranium-238 ions are heavier and bend less in the magnetic field, while uranium-235 ions are lighter and bend more. This separation allows the isotopes to be collected separately at the end of their paths. Special containers collected the separated isotopes based on their different paths. Simply put, it just separates them. Now, one of the most prominent methods of uranium enrichment was at the K25 gaseous diffusion plant. The K25 plant had one major advantage over Y12. The gaseous diffusion plant could produce more enriched uranium at less cost. It actually had greater efficiency than the Y12 plants, and it actually led down to the shutdown of many of them. Gaseous diffusion is a way to separate different types of uranium using their weight differences. And I'm going to try to give this in a simple explanation. So the basic principle is that lighter gas molecules will go through tiny holes in a barrier faster than heavier ones. So in a gas with both uranium-235 and uranium-238, the two types of uranium, the lighter uranium-235 goes through the holes a little bit easier than the heavier uranium-238. Since the weight difference between uranium-235 and 238 was tiny, the gas had to pass through many barriers, one after the other, to gradually increase the amount of uranium-235. Now, pure uranium is very hard to work with because it needs very high temperatures to turn into a gas. So the solution they came up with was to use a compound called uranium hexafluoride. It's made of one uranium atom and 6 fluoride atoms. The weight difference in uranium hexafluoride molecules comes only from the uranium part, making it easier to separate U-235 from U-238. Uranium hexafluoride is a solid at room temperature, but turns directly into a gas at 56.5 degrees Celsius without becoming a liquid first. This makes it easier to handle during the enrichment process. Now, while this process worked very well, it also did have its problems. Choosing the right barrier was a big challenge. The barrier, more like a superfine filter, had to have billions of tiny holes, much smaller than a molecule's typical size. It had to be delicate enough to tell the difference between U-235 and U-238 isotopes, but also strong enough to handle high pressure and the wear and tear of being put together. The barrier had to resist corrosion from uranium hexafluoride gas, a substance that could easily damage materials, contaminate the gas, or block the tiny holes. No air could also leak into the system. Air moisture would react with the gas, creating a compound that would block the holes and stop the whole process. Now let me put this into perspective. A plant producing 1 kilogram of uranium-235 a day would require acres of barrier area and thousands of stages, but the process would be continuous, not in a batch. Gaseous diffusion offered less likelihood of mechanical difficulty than any other methods, such as a centrifuge. Another method was at the facility S50, and they did liquid thermal diffusions. Liquid thermal diffusion is a method that separates different types of uranium using temperature and how they move in a liquid. They use two big, hollow, tube-like pipes, one inside the other, and filled the space between them with liquid uranium hexafluoride. Since fluoride only has one type, the weight differences in the molecule are due to the uranium part, just like the gaseous diffusion. The outer pipe was kept cool, attracting the heavier uranium-238, and the inner pipe was heated, attracting the lighter uranium-235. Because of the temperature difference, the liquid moves in convection currents that gradually make the lighter U-235 concentrate more at the top of the pipes. The more concentrated uranium-235 at the top was then collected. The taller the pipes, the better the separation, as it gave more room for the lighter uranium-235 to separate and move upwards. Also, this facility produced an enriched mixture in which the percentage of uranium-235 was raised from 0.71% to about 0.852%. So not that much. Now you can look at the dates on when they started this facility and the other ones, but really this one would send their enriched product to the Y12 and the K25 place. Now there was another method they were considering, and that was gas centrifuges, but they faced a lot of challenges. There was a lot of underperformance compared to theoretical predictions, and to scale everything up for effective production just wasn't viable. It works exactly how you think it is. You see the axis of rotation in the center, and when it's spun around, the uranium-235 would be closer to the axis of rotation, and uranium-238 would be on the exterior, further away from the axis rotation. So basically, they just separated it that way. This method was also pretty garbage at the time, so I'm not really going to go in depth about the explanation because, again, it's just garbage. Believe me, it still works, it's just not really as efficient as the other methods. So if you look at this picture here, you can see it kind of goes into a flow chart of how they went from a small percentage of uranium-235 all the way up to 90, which was used in the atomic bombs. Now, while the K25 facility was more efficient in terms of volume of uranium it could process and enrich, it would essentially go to Y12 to process it up to that high 90%. It employed like tens of thousands, probably even more, just to get a small amount of uranium-235 for the first atomic bomb in the Manhattan Project. It's crazy to think how much work went into it. Now I know you're thinking, well, what about plutonium? How did they get that? Oh, don't you worry. I will go in depth about how they did that as well. Actually, I feel bad, guys. This is a chemistry channel. I should be teaching you some chemistry. How do they even make these uranium compounds? Well, first, we have to go get some uranium ore. Once we have the ore, we can then proceed on to the next step. We first have to crush and grind the ore to liberate the mineral particles. After we do that, we then need to make something called yellow cake, and we're going to go through the reactions to get there. Now there is a bunch of minerals in uranium ore, one of the major ones being called uraninite. Now uraninite is a radioactive uranium-rich mineral and ore with a chemical composition that is largely uranium dioxide. Now there's a term called leaching, which basically means that uranium ores are leached of their uranium values by usually acidic or alkaline aqueous solutions. Now if you want the leaching to be successful, uranium must either be initially present in the more stable hexavalent state or oxidized to that state in the leaching process. Sulfuric acid is generally used as the leaching agent, and they'll also add manganese dioxide or chlorate ions to oxidize the tetravalent uranium ion to the hexavalent uranyl ion. In a nutshell, the oxidized uranium reacts with the sulfuric acid to form a uranyl sulfate complex anion. You'll also notice that this starts with uranium trioxide, and I mentioned that there was a lot of uranium dioxide in the uraninite. Basically, this just needs to be oxidized to its hexavalent state. And that's why you see uranium trioxide in its hexavalent state in the reaction. Now, there's a couple different methods to concentrate and purify the uranium. One is an ion exchange, and the other is a solvent extraction. Solvent extraction is a more common method, and it uses tertiary amines in an organic kerosene solvent in a continuous process. First, the amines, which we can just say is R3N, reacts with the sulfuric acid. Then, the amine sulfate extracts the uranyl ions into the organic phase, while the impurities remain in the aqueous phase. The uranylamine complex then reacts with ammonia to give ammonium diuranate. The ammonium diuranate is then heated and it's converted to uranium oxide, commonly known as yellow cake. Now, once the yellow cake is at the refinery, it's actually dissolved in nitric acid, and the resulting solution of uranium nitrate is fed into a continuous solvent extraction process. The uranium is extracted into organic phase, which is just kerosene, with tributyl phosphate, and the impurities again are in the aqueous phase. So after that purification, the uranium is then washed out with the kerosene and some dilute nitric acid and concentrated to evaporation to the pure uranium nitrate. After that, all they do is just heat it to the pure uranium trioxide. The pure uranium trioxide is reduced with hydrogen in a kiln. This creates uranium dioxide, and then it's reacted with hydrogen fluoride to form uranium tetrafluoride. The tetrafluoride is then fed into a fluidized bed reactor and reacted with gaseous fluorine to obtain the hexafluoride. Once you have the uranium hexafluoride, then this is when we can separate the isotopes. Now that we got that out the way, we can actually go on to plutonium. Now, plutonium during the Manhattan Project was produced at Hanford's B reactor. Plutonium, which is a silvery gray radioactive metal, is technically considered man-made. Now, scientists have found trace amounts naturally occurring, but it was from highly unusual geological circumstances. So, plutonium is formed actually starting with uranium-238. Now, uranium-238 transforms into plutonium-239 through a series of nuclear reactions, generally inside a nuclear reactor. First, there's a neutron capture. Uranium-238 absorbs a neutron from the reactor environment, becoming uranium-239. This process adds a neutron to the uranium-238 nucleus. The newly formed uranium-239 is unstable and undergoes a type of radioactive decay known as beta decay. In this process, a neutron in the uranium-239 nucleus is converted into a proton while also releasing an electron and an antineutrino. An antineutrino is a particle that carries away energy and momentum. The uranium-239 then changes into neptunium-239. Neptunium-239 is also unstable and undergoes beta decay similar to uranium-239. Another neutron is converted into a proton, and an electron and an antineutrino are released. This transformation changes neptunium-239 into plutonium-239. Now, plutonium-239 is a fissile material, meaning it can sustain a nuclear chain reaction, making it valuable in nuclear reactors and atomic bombs. Now at Hanford, plutonium was produced in nuclear reactors specifically designed to make plutonium. B, D, and F reactors were the first full-scale plutonium production reactors in the world. The B reactor was the first to become operational. Now, the reactors were graphite moderated and water cooled. Natural uranium rods were inserted into a large graphite block, and water flowed through the channels to remove heat generated by nuclear fission. In natural uranium, the interaction between fertile uranium-238 and neutrons give rise to the production of plutonium-239, a process that is essential for breeding new fissile material. Concurrently, the uranium-235 present in the natural uranium mixture maintains the critical chain reaction, providing a continuous supply of neutrons. These neutrons are not only pivotal for sustaining the reaction, but also for facilitating the transmutation of uranium-238 into plutonium-239. As the concentration of plutonium-239 increases in the reactor, it also undergoes fission. Now, what's really interesting is the production of plutonium isotopes occur at a slower rate than plutonium-239. Thus, uranium that has been in the reactor for a short period of time has a significant amount of plutonium-239 relative to the heavier plutonium isotopes. And actually, the fuel rods are only in there for a specific amount of time to maximize the plutonium-239. Now, in case you didn't know, it takes a huge amount of uranium to produce a tiny amount of plutonium. To give you a comparison, it would be like the weight of an elephant being converted to the weight of a small kitten. Now, because of the low concentration of plutonium, plutonium compounds cannot be precipitated directly. Thus, any separation process involving precipitation had to be based on co-precipitation techniques that employed carriers for plutonium. Now, the bismuth phosphate process was first used for the large-scale separation of plutonium from uranium and the fission products. Basically, it was a selective co-precipitation of plutonium 4 plus from an acid solution by a bismuth phosphate carrier and the ability of plutonium 6 plus to remain in solution in the presence of that bismuth phosphate carrier. And hey, here comes the chemistry again. Okay, I'm going to run some things by you really quick. If you see X, that just means fission products or uranium. If you see the superscript Y+, that just means the oxidation state of the fission products or uranium. Okay, very quickly, the neutron irradiated aluminum clad fuel rods were removed from the reactor to a pool of water. They remained there for a couple of days. Then the aluminum casing was removed from the rods with a concentrated sodium hydroxide solution. And then we can start what happens. First, the fuel rods were dissolved in nitric acid, and then after the addition of the sulfuric acid to keep the uranium and other fission products in solution, plutonium 4 plus was co-precipitated with bismuth phosphate. The precipitate containing the plutonium was then dissolved in nitric acid, and the plutonium 4 plus was oxidized to plutonium 6 plus with sodium dichromate. This time, plutonium remained in the solution as plutonium 6 plus, while any residual uranium and other fission products were precipitated with the additional bismuth phosphate. The plutonium 6 plus was then reduced to plutonium 4 plus, and the cycle was repeated. At this point, the carrier was changed to lanthanum fluoride, and a similar oxidation reduction cycle was performed to achieve further purification and concentration of the plutonium. Now, the concentration of plutonium was high enough so that no carrier was required for the final purification step, which was the precipitation of plutonium peroxide from a basic solution. I don't have it pictured here, but the peroxide was converted to a plutonium nitrate paste that was shipped to Los Alamos. The overall recovery of plutonium by this process was greater than 95%. It also generated huge amounts of chemical and radioactive wastes, which was kind of a problem. But hey, not my problem though. Now there is an updated process called the Purex process, and if you want to learn more about it, you're very welcome to go look it up online. I just won't be explaining it in this video. I've been yapping a little too much, and I think it's time that we actually start talking about how the bombs work. Starting with the little boy atomic bomb, there's a couple key things that we need. First off, we need a high amount of uranium-235. That's why they went through so much trouble to separate the isotopes. Like mentioned before, uranium-235 is fissile, and uranium-238 isn't. The reason why we need such a high uranium-235% is if we had a high uranium-238%, it would not undergo fission. We need the fission to happen so more neutrons are released and it hits more uranium-235 nucleuses, and then even more fission happens, right? So if we don't have that, not much is going to happen. Also, if you look at the picture above, on the right-hand side, there's a neutron not hitting anything, which is also another reason why we need a bunch of uranium-235 to increase the chances of it hitting. Now, they also have neutron reflectors inside of the atomic bomb, but we'll discuss that a little bit later. I also mentioned earlier in the video about the subcritical, critical, and supercritical masses. It's also important that we hit the supercritical mass. Now, it is pretty hard to load an atomic bomb with supercritical mass, so they actually designed a gun-type design. Essentially, two subcritical masses of uranium are at either end of this gun barrel design. One is shaped like a bullet, while the other is a hollow cylinder target that just fits around the bullet. Now, conventional explosives, which they don't say it on here, but it's just cordite by the way, and it will shoot the bullet down the gun barrel where it mates with the target. Once the two subcritical masses are brought together rapidly, it forms a supercritical mass, resulting in a chain reaction and an atomic explosion. Now, the atomic bomb already has more than a critical mass worth of uranium, but it's divided into two pieces. The reason for this is that the neutrons are too far apart to cause fission in one another. That would really suck if both halves went together when you weren't expecting it. Hopefully that's never happened before. And like mentioned previously, they had neutron reflectors in there, which were generally tungsten carbide and steel. These were the compounds used in Little Boy, but there's other neutron reflectors like beryllium. This would reflect neutrons back to the uranium core, increasing the fission efficiency. Now, the plutonium bomb was actually a little bit different. Now, unlike what most people think, plutonium was actually used in the Trinity test when the first atomic bomb went off. This design was an implosion assembly method. Now, plutonium is a really good fuel for nuclear bombs, but it's a little bit harder to ignite than the uranium-based ones. Now, the plutonium is fashioned into this spherical core, and it's known as the plutonium pit. It's placed at the center of a hollow shell of conventional high explosives. It's also called the explosive lens, if you wanted to know that. These explosives must detonate at the same time to form a spherical shockwave to compress the pit, reducing the critical mass. In its normal state or uncompressed state, it has less than critical mass. But once the explosions go off, the increased density results in a supercritical mass and an explosion. Now, it's not pictured on here, but there is a neutron initiator at the center of the core to release neutrons to start that nuclear chain reaction. Now, this neutron initiator actually had a code name called the Urchin. Essentially, this would be located in the center of the bomb's plutonium pit. It consisted of a beryllium pellet and a beryllium shell with polonium between the two. The pellet was around 0.8 centimeters in diameter and was coated with nickel and a thin layer of gold. The beryllium shell was of 2 centimeter outer diameter with wall thickness of about 0.6 centimeters. The inner surface of that shell had 15 concentric wedge-shaped latitudinal grooves and was, like the inner sphere, coated with gold and nickel. A small amount of polonium-210 was deposited in those grooves of the shell and on the central sphere. Basically, the layers of the gold and nickel serve to shield the beryllium from alpha particles emitted by the polonium. Essentially, when the shock wave from the implosion happened, it crushes the initiator. Hydrodynamic forces actually acted on this groove shell and would mix the beryllium and polonium, allowing the alpha particles from the polonium to impinge on the beryllium atoms. Reacting to that alpha particle bombardment, the beryllium atoms would emit neutrons at a rate of about 1 neutron every 5 to 10 nanoseconds. This would then trigger the chain reaction in the compressed supercritical plutonium. They also used a combination of fast and slow explosives. Fast explosives would detonate in a very short time frame and was used to initiate the implosion. This provided the initial shockwave necessary to start compressing the core. The slower explosives have a longer duration of the explosion. These explosives were shaped and positioned around the plutonium core to create a converging shockwave. The precision in the shape and the timing of the detonation of these explosives were crucial for achieving a symmetrical implosion. Any asymmetry in the explosion wouldn't be efficient, or not even go off. Now that you know how these work, let's take a look at what they look like.
Now I am become death, the destroyer of worlds.
And with that, I just want to thank you so much for watching. I put a huge amount of effort into this video, so please enjoy it. If I have anything wrong, please put it down in the comments. I will read it, and I will correct the information in a pinned comment. And if you guys want the science of hydrogen bombs, let me know, and I can go over that too. Other than that, have a good day, and hope you learned something.